Hello everybody, welcome to this video. Here today we are going to calculate the Fourier coefficients of the Fourier series for a rectified sinusoid. So what is this rectified sinusoid? Well, typically in electronics and electricity we have a point where we may have a sinusoidal AC signal like this one. For example, this could be the average value, and then we would like at the other side to have a rectified, so meaning that it has only positive periods of the signals like this, so the negative is rectified to be positive, so instead of going that way over here it goes upwards and so on. So this is a rectified sinusoid. Typically this is done with a block that you will study in electronics, which is called a bridge, a rectifier bridge, which consists on a group of diodes. Several diodes over here, they configure the bridge and they achieve this. The negative parts of the sinusoids at the input get rectified and goes into a positive lobe, as you can see over here. So, for example, mathematically, in the input, if we got, for example, x equal to cos t, cosinus of time, at the output, typically, what you get is y of t, a signal which is the absolute value of x of t, which goes into absolute value of cosinus of t. So what we have to do is to get the Fourier series coefficient of the signal. If we are more, let's say, detailed, we plot x of y of t, this sinusoid rectified, what you get is what we have plotted over here. If it is a rectified cosinus, so you have the positive part of the cosinus, and then the negative part, instead of going that way, it gets rectified and goes over here, and also in negative t's over here. Okay, so typically this would be half pi minus half pi, and the maximum value of the cosinus is 1, so this will be 1. And again, the period that this goes repeated is a period of p. So in the rectified cosinus, kind of halves the period, and instead of being 2p, in this case the period of the rectified cosinus is not 2p but it's p. So the angular frequency, what we call in the theory omega sub 0, is 2p or 2 pi divided by capital T, by the period, and in this case is 2 pi divided by pi. So in our case this will be p radians per second, assuming that the time is measured in seconds. Okay, so what they are asking for is which are the coefficients of the Fourier series of this signal. We call them a sub k, and the formula that helps us to calculate is 1 divided by the period of the signal, integral extended to any period I want to choose, of the signal times the exponential of minus j k omega 0 t. And we integrate in time. In this case, we are going to choose this period, the period that goes between minus half pi and plus half pi, and the period we have calculated that this is p, so this will be 1 divided by the period, which is p, integral between minus pi divided by 2 plus pi divided by 2, and x of t in this period, x of t is the positive part of x of yt, so it will be cosinus of t. Okay, if I had to pick another one, it will be cosinus of t, but somehow shifted to the right or to the left. Okay, times a minus j k omega 0. We have seen that omega 0. Sorry, this is wrong. This is 2. Okay, so omega 0 2 times t dt. Okay, And to do this integral, it's there are several ways. You can try several methods, but the easiest one is just to write the cosinus as exponentials, complex exponentials, which it's in this case it will be exponential of jt plus exponential of minus jt divided by 2. Okay, so if we put that in the exponential, in the integral, is a very easy one. It's an immediate one, so it's just 1j divided by 2p, and then we have two terms here, which is the first one is 1 minus 2k exponential of j times 1 minus 2k half pi divided by 2 minus a exponential that minus j1 minus 2k pi divided by 2, and then we have another term here with a minus in the front, and then we have here down 1 plus 2k, and here we have e minus j 1 plus 2k pi divided by 2 minus exponential of j 1 plus 2k. Let me go a bit to the here in the paper. Here we go. Pi divided by 2. Okay, so this is, I haven't done in detail, but this is an immediate integral, and this is applying the barrow, the two limits, up and down. This is what you get. So now the trick to simplify this is very easy. It's just to realize that we have this type of exponentials all over the place, which is e exponential of j times 1 minus 2k times pi divided by 2, and if you divide this exponential in 2, you get the first is ajp divided by 2 times the second is a minus jk pi, and here you just realize that the exponential of j pi divided by 2, this is j, and the exponential of minus jkp, you can see that this is minus 1 to the k, because what you have is exponential of minus j pi, which is exponential of minus j pi to the k, and j pi is minus 1. So well, you should be aware of that from your classes in complex algebra. So in summary, this exponential goes into j times minus 1 to the k. So this gets simplified, and at the end, if you play with this trick around, what you will get is this form for the coefficients, which is 2 divided by pi minus 1 to k divided by 1 minus 4k squared. Okay, so these are the coefficients of the Fourier series of rectified cosinus. Remember that it's important always to check that when we apply this formula to k equal to 0, that is a sub 0, which is the coefficient that corresponds to k0, that is a very important one, because this has to do with the average power of the signal, the DC power. You have to make sure that this gets well calculated using this formula. If you calculate using this formula, putting k equal to 0, their solution is 2 divided by pi, which again, this is the average value or the DC part of the signal, which is okay. Why do I do that? Because sometimes the general formula that you come up with applying the definition of the integral doesn't fly, doesn't work well, and you may get an indetermination or something strange. So it's a good exercise to try this. If you had a result that is not meaningful, meaning plus, minus infinite, or an indetermination, what you should do is you have to go back and calculate A0 directly with the formula, okay, with the formula, but putting here directly k equal to 0, which makes a 1 over here, and then you calculate this directly. okay, in case that calculating for a general k and then putting k equal to 0, then you get an indetermination. Okay, so finally, if the exercise was not only to get the coefficients but to show actually the series, this will be, well, we call it y of t, which is the absolute value of cosinus of t. This finally is summatory in the k index of the coefficients a is k times the exponential of j omega 0 t, and if we put the values that we got, we would get summatory. We can put even all the coefficients, which are coming from minus infinite and going up to plus infinite, of 2 divided by pi, then minus 1 to the k, I'm just copying this formula here, divided by 1 minus 4k squared, and times a exponential of j k omega 0, which is 2t. Okay, this will be the series coefficients, or the series, the Fourier series of the rectified cosinus. Well, I hope that was clear to you. That's a nice exercise to practice the formulas and some integration, and see you in the next video. Bye-bye.